Let's start this very interesting discussion about multi-dimensional heat transfer. So, the heat flux is given as minus k dt by dx. If we bring the A into the denominator of Q, so that would become the heat flux, as we were looking a couple of slides earlier. Now, if we, in addition to x, also consider y and z, right? So then Qy, heat flux in y direction, would be written as minus k times delta t over delta y, or dt over dy, and similarly the heat flux in z direction will be given as minus k delta t over delta z, or dt over dz, where this dx is the thickness, or delta x is the thickness of the medium in x direction, delta y is the thickness of the medium in y direction, and delta z is the thickness of the medium in z direction. Now consider this block, right, or a box, right, or a wall. In fact, this is a wall. It is a plane wall because it has got the three dimensions x, y, and z. And if we consider this dimension as this dimension, which is 7, as x, right, and if we consider this dimension, which is 3, this length, as the y direction, and if we consider this height, which is 2, as z axis. So in fact, we are considering 3 dimensions, 3 axes. This is the x-axis, the longest one is x-axis 7, and this is the y-axis 3, and this 2 is the vertical is the z-axis. Now if we consider qx, so the heat will flow from this face, right, when the heat will flow in this direction, when the heat will flow in this direction, allow me to draw it. When the heat will flow in x direction, it will in fact be moving from this face, the area of which is 3 by 2, to the other face, which would be on the other side, having the same area. Right now we are considering the same area. So this would be the heat transfer in x direction. When we consider the heat transfer in y direction, for example, if we consider the heat transfer in this direction, because this is our y-axis, we have just said that this is the length in, this 3 is the length in y. So if we consider heat transfer in y direction, then the heat will be transferred in this direction, means from this face, having an area of 7 by 2, to the face which is on the back side, which is on this back side. Again, the heat is not being transferred from an edge to the other edge, it is being transferred from a face to the other face, from one surface to the other surface. So the heat will be transferred from this face to the face on the back, right, and there would be infinite planes in between. And the heat will then reach on the back face. So this is what we call Q in y direction. You may notice that the area in x direction is not the same as the area in y direction. The area in x direction is in fact 3 by 2, because when we say area, when we say Q is minus Ka delta T over delta x, then A is the area which is normal to the direction of heat flow, and when the heat is flowing in this x direction, then it will the area which will be normal to this heat flow or heat flux would be 3 by 2, right? So this would be what you may call Ax, with x in the suffix of A. Why we are calling it Ax? Because we are discussing that areas in all the 3 dimensions may not be the same all the time. So when we consider Q in y direction, then the area which is normal to the heat flow or normal to the heat flux, this would be the heat flux or heat flow. So the area which is normal to the heat flux is in fact 7 by 2. So this AY is not the same as AX. This would be AX, right? And you would have realized that AX does not have X in it. Means AX is in fact the length in Y multiplied by the length in Z. Similarly, this area would be AY, and AY does not have Y in it, Y dimension in it or Y length in it, because AY is in fact the product of the length in X and the product of and the length in Z. And then QZ. So QZ would be the heat transfer in Z direction. So it may be from the bottom edge to the top edge, or it may be from the top edge to the bottom edge. So if you allow me, I will take it in this direction for your convenience, because what you can see is the top edge. So if the heat is transfer is flowing in this direction, then we will call it QZ. So now this is consider those circles as filled up. Do not consider it as a hollow block for the time being. So now the heat will flow from the top face to the bottom face, right? Or from the bottom face to the top face. And in here AZ would be this length which is in Y multiplied by this length which is in X. So you can see over here that AX, AY and AZ are all different quantities. They may be the same if it is a cube, and they may be different if it is not a cube, if it is a cuboid. So when we have multi-dimensional heat transfer if the heat transfer is only taking place in one dimension, we call it, for example, in X only, we call it 1D heat transfer. If it is taking place in 2 dimensions, X and Y, we call it 2D heat transfer. And if it is taking place in all 3 dimensions, we call it 3D heat transfer or 3-dimensional heat transfer. See, the heat flow in any particular direction will depend upon its temperature difference. So for example, if this face is at a temperature of, for example, 100 degrees Celsius, and the face on this side, which would be opposite to this one, has a temperature of 30 degrees Celsius. So then the heat will flow in X direction, right? But if this face and this face do not have a large temperature difference or no temperature difference, then the heat will not flow in Y direction. Similarly, if the top face and the bottom face are almost at the same temperatures, so then the heat will also not flow in Z direction. So heat will flow in any particular direction depending upon the temperature difference. So we may have the case of one-dimensional heat transfer or multi-dimensional heat transfer depending upon the temperature differences. Now, when we have multi-dimensional heat flow, let's say the heat is being transferred in all the three dimensions, X and Y and Z. So the heat will flow in X direction depending upon the temperature difference in X direction. Depending upon the temperature difference in X direction means what temperature do we have over here and what temperature do we have at the other end. If the temperature difference between this face and this face is smaller, the heat flow would be smaller. And if the temperature difference between these two faces is large, then more heat will be transferred. So the heat transfer in fact depends upon the temperature difference, right? So it is also not necessary that Qx and Qy and Qz are all the same. They have all the same values. It is not necessary. Qx may have a different value, Qy may have a different value, and Qz may also have a different value depending upon the temperature differences. The larger the temperature, depending upon the temperature differences and depending upon the thicknesses of the medium, delta X and delta Y, and delta Z. Right? So over here, depending upon the variation in T, depending upon the variation in temperature in x direction, depending upon the variation in temperature in x direction, the heat will flow. Means it will depend what temperature is at this phase and what temperature is at the other phase. What I am trying to figure out over here is the same thing that we had seen a while ago. Right? What is how does the temperature vary? So if the temperature variation is more, more heat will be transferred, and vice versa. So there is in fact a temperature pattern. There is in fact a particular temperature profile, temperature distribution. Means T as a function of x. Means T as a function of x. So in x direction we would have T as a function of x. And what would it mean? It would very simply mean that how does temperature vary in x direction? It only means, and it very simply means, how does temperature vary in x direction? For example, if this is the temperature variation that we have in x direction, what does this mean? It means that T1 and T2 are the same. And if T1 and T2 are the same, then no heat will be transferred in x direction, right? So what I am trying to emphasize is that we would have a temperature profile. We would have a temperature distribution depending upon the temperature values at the two phases, and also depending upon the thickness of the medium, and also depending upon the nature of the medium itself, which we will see later. So coming back where we were at, right? So now there would be a temperature profile between this phase and the opposite phase. Right? So there would be T as a function of x. Right? Now when we come in y direction, there would be a temperature on this phase and a temperature on the back phase, and there would be a temperature profile between these two phases, this phase and the back phase. Means we would have a T as a function of y. We would have a T as a function of y. We would have temperature as a function of y. And what would that mean? It would very simply mean that how does temperature vary in y-axis? It may vary linearly as we were looking at the variation, as we were looking at the linear variation in x, but it may have different attributes. For example, it may have the same form of y is equal to mx plus c with different values of m and c. Right? For example, if y is 2x plus 3, and if y is 10x plus 11, now the temperature distributions have similar forms. 2x plus 3 and 10x plus 11, they have similar forms. They both are linear, right? But they have got different attributes. That if we plot the two equations, they won't be the same. Right? 2x plus 3 would have a different plot than 10x plus 11. Right? So, coming back to our discussion, we would have T as a function of y, and similarly there would be T as a function of z. Means how does temperature vary in z-axis? How does temperature vary in height? So now T would be a function of x and a function of y and a function of z. So when the temperature would depend upon more than one parameters, so it's better to use Dava sign instead of D, because Dava represents partial variation. You probably would know the difference between D and Dava if temperature depends only upon one parameter. If temperature depends only upon x-axis, so and not on y and not in y or z-axis, means if T is a function of x only. Now, if T is a function of x only, it means that it is the case of one-dimensional heat transfer, right? And if T is a function of x and y and z, now this makes a three-dimensional heat transfer case. And if T is dependent upon x and y and z, So that would make it a case of partial differentiation. So we should be using the word, not the word, should be using the letter dava instead of the letter d, just to denote that now t is depending upon more than one axis, more than one parameters, means x as well as y as well as z. Now if it is a multi-dimensional heat transfer case, then we can write q as minus k times I dava t by dava x plus j dava t by dava y plus k dava t by dava z, where I, j and k are unit vectors, and then we can write q as minus k del t. However, if it is a one-dimensional heat transfer problem, then it would only be minus k delta t over delta x or dt by dx. If it is one-dimensional heat flow, then we would not be writing it as minus k dava t by dava x. If it is one-dimensional heat flow, then we would be writing it as minus k dt by dx. So now we would have in this case we would have t as a function of x, y and z. If it is a multi-dimensional heat transfer case, means t would have a different variation in x and in y and in z. So we would be having an equation such as t is equal to 2x square plus 3y plus 5z. So though we would be having those sorts of equations which will tell us that we have got the multi-dimensional heat transfer case. So now P would be varying in x, y and z directions. Now in addition to x, y and z, the temperature may also vary in time. It may not vary in time. What does this mean? It means that we are talking about steady state heat transfer or transient heat transfer. So if, for example, T1 is 100 degrees Celsius and if T2 is 30 degrees Celsius. So if T1 remains around 100 degrees Celsius and does not change with time, whether you check it now or after a couple of minutes or after a couple of days or after a month or after 6 months, and the T1 remains the same, and similarly if T2 remains the same as well, so that would make it the case of steady heat transfer. So the properties, and by properties we mean the temperature in heat transfer. If the temperature is not changing with respect to time, now at a particular location, this is very important because of course the temperature would vary with location. If the temperature does not vary with location, the heat will not be transferred. So so the temperature would vary from location to location, but at a particular location, for example at this x, at a particular location, if it is not changing with time, or at this location if it is not changing with time, so then this heat transfer would be termed as steady. And if T1 at this instant is 100 and after 1 hour it becomes 90, so then it would not be the case of steady heat transfer. We will call it non-steady or transient heat transfer. Means the properties, rather the temperature would start varying with time at a particular location. So we may come across, and we will come across, those situations where T would be varying in x, y and z, and along this variation in space, there would be variation in time. So capital T would be used to represent the temperature, whereas small t will be used to represent time. So if this is the case, so then we would have a dava t by dava x, dava t by dava y, dava t by dava z, and dava t by dava t. Dava t by dava t means dava of capital T by dava of small t, means the variation of temperature with with time. This is what we have already covered. Over here it says composite wall. We will come across composite wall later. Composite wall is the wall which is composed of more than one material. Right? So different materials would have different thermal conductivities, which will change the amount of heat transfer even if they have the same thicknesses. We will come across composite walls later. Now, the last thing before we start convection is thermal diffusivity. Thermal diffusivity is in fact a ratio of the heat conducted to the heat stored. It is the ratio of the heat conducted to the amount of heat stored. And just like thermal conductivity, it is a material property. Kindly note, it is very important point that thermal conductivity is a material property and thermal diffusivity is a material property as well. So every material would store energy, okay? And you will find a very important sentence over here. Let's first discuss what is written over here. We have got the Cp, which is the specific heat, which has got the units of joules per kg per Kelvin or per degree Celsius. Because again, specific heat is defined as the amount of energy required to raise the temperature, required to change the temperature of a unit mass of a substance by a unit Kelvin. So the change in temperature in Kelvin is the same as the change in temperature in degree Celsius. So therefore Cp may have the units of joule per kg per degree Celsius or joule per kg per Kelvin. They both would be the same. And if we multiply it by density, if we multiply Cp by density, then it would become per unit volume. Right now Cp is in per unit of mass. So when we multiply joule per kg per degree Celsius by density, density means kilograms per cubic meter. So this kilogram will get cancelled out and we would have volume in here. So that then it would become a unit volume basis. And this is what we call heat capacity. So rho times density times Cp is called the heat capacity. Sometimes we would also be multiplying Cp with mass later. So now thermal diffusivity is a material property. First of all, it is very important that it is a material property. It depends upon the nature of the material, just like the thermal conductivity. Thermal conductivity depends upon the nature of the material, which appears in the transient heat transfer. And what does it mean? It represents how fast the heat diffuses through a material. So it tells us how fast the heat diffuses through a material, and it is a property that will be used in transient heat transfer analysis. And it is in fact a ratio of the amount of heat conducted to the amount of heat stored. And amount of heat conducted means K and the heat stored is rho C. Now what happens is that every material stores energy, right? Every material stores energy. So when we supply heat to a material, some part of it will get stored and some part of it will get conducted, will move forward. Now the amount of the energy stored will depend upon its storage capacity, upon its heat capacity, upon its specific heat. So the heat will be stored till a certain period of time. Let me give you an example. Let's say if we have a pipe carrying steam at consider that the pipe, you have just brought the pipe in and the pipe is at room temperature, or you have just started the boiler and the pipe is at the room temperature of 30 degrees Celsius, and the steam which is flowing through the pipe is at 400 degrees Celsius. So when the steam would start flowing through the pipe, at time t is equal to 0, then the the material of the pipe will start storing some energy. The heat will flow from the pipe to the steam will the heat will flow from the steam to the pipe. The heat will flow from higher temperature steam to lower temperature pipe, and all the energy will not be conducted. Some of the energy will be stored, and as a result of this storage, we will feel, or we will see, that the temperature of the pipe will start going up. The temperature of the pipe will start increasing from 30 to 40 to 50 to 100 to 150 degrees Celsius. And then, how the temperature of the pipe is increasing? Because it is getting energy from some source, and that some source is steam, and the pipe is in fact storing energy. So whenever there is storage of energy, the temperatures will not remain same. Whenever there is a storage of energy, either in negative terms or positive terms, the temperatures will not remain the same. This is a very important point. And hence, if the temperatures do not remain same at a particular point, at a particular position, that would be the case of transient heat transfer. That would be the case of transient heat transfer. So, let's say the steam is flowing as at 400 degrees Celsius, and the temperature of the pipe is increasing from 30 to 50 to 80 to 100 and then to 150, and then at 150, of course, it will not keep on increasing forever. There would come a time when the temperature of the pipe will cease to increase, will stop to increase. And suppose that the pipe temperature goes up to a maximum of 150 degrees Celsius, after which its temperature does not go beyond anymore. So now the steam is continuously flowing through the pipe. However, the steam and the heat is also being conducted into the pipe, but the pipe is no more storing energy. The pipe is no more storing energy. Rather, it is conducting all the heat from one end to the other, and then to the air, if the pipe is a bare pipe, if it is open to atmosphere. So there would be a certain period of time where the temperature would vary. There would be a certain period of time where the temperature will not remain constant. For example, from 30 degrees Celsius to 150 degrees Celsius, the temperature of the pipe was constantly increasing. So this period would be called a transient heat transfer period, right? And after that, the system would attain a steady state, because the temperature of the steam is 400 and the temperature of the pipe is 150, and the temperature of the pipe is not increasing anymore. So now the system would be termed under a steady state. So you may say that every steady state system passes through a transient state before it attains steady state. Let me give you a very simple example. Let's say you are in a room. The temperature of the room is suppose 35 degrees Celsius, and when you turn the air conditioner on and you set that air conditioner at, let's say, 20 degrees Celsius, so the temperature of the air will not become 20 degrees Celsius at once. It will gradually come down from 35 to 34 to 33, 32, 31, 30, 25, and then 20. And then when the temperature of the air would be around 20 degrees Celsius, the sensors in the air conditioner would sense it, and it will then turn it off. And when and then it would try to keep the temperature of the air around 20 degrees Celsius. Whenever it goes even a little bit above 20, it will again turn the air conditioner on, so as to bring it around 20 back. So while the temperature of the air was decreasing from 35 degrees Celsius to 20 degrees Celsius, the system, means the room, the air was in transient state. And when the air reached 20 degrees Celsius and it was being maintained around 20 degrees Celsius, so we would call it a steady state system. So over here, so this was an example where I was trying to clarify that every system goes through a transient system before it attains a steady state, right? Now, alpha, which is the thermal diffusivity, tells us how fast the heat diffuses through the system, and it is the ratio of the energy conducted through the system, through the material, to the energy stored. So whenever there is energy stored, we would be talking about transient heat transfer, right? Because the energy storage in positive or negative terms, positive or negative terms means energy coming in or energy going out. So energy storage would always result in a change in temperature at a particular location, which would make the system transient, right? Now, the thermal conductivity represents how well a material conducts heat, whereas the thermal conductivity represents how well a material conducts heat, where the heat capacity represents how much a material stores energy. So it is a ratio of the energy conducted by the medium to the energy stored by the medium. Of course, a material which has a high thermal conductivity, higher K, or a low heat capacity would be having higher values of large thermal diffusivity. So if it is having large thermal diffusivity, what does this mean? It means that it will keep less, it will retain less and transfer more. It will keep less and transfer more. This is what is meant by higher thermal diffusivity. A small value of thermal diffusivity would mean that the heat is mostly absorbed by the material. So a small thermal diffusivity means that the heat is not being diffused by the material. Heat is not being diffused by the material means whenever the heat is being supplied to the material, it is keeping it, it is absorbing it, and a small amount of heat is being conducted further, and a small amount of heat is being conducted further. So this is what is meant by thermal diffusivity.